All right, so let's start Unit 12 in class. This is Chapter 16 in your textbook, and we're going to go over 16.1 and 16.4 in this video. All right, so we're going to talk about the three laws of thermodynamics in Chapter 16. So it's essentially explaining whether or not processes are going to be favorable, if they're going to be spontaneous, if they're going to happen by themselves, or if they need outside influence. Very important concept, because if they need outside influence, that influence is coming from you and I, the chemist, and that's going to cost us money. So it's always important to try to find reactions that'll kind of work on their own. And that makes them self-sufficient, and they need less prodding by the outside influences, and thus that makes them a bigger candidate to operate independently. All right, so let's talk about the first law of thermodynamics. That is the law that you've heard before. It is probably the most fundamental law, and it's that energy can neither be created nor destroyed. So the law of conservation of energy, correct? And this just simply says that the energy of the universe is constant, so it's never ever changing. This kind of limits the amount of energy that we can produce, because we need to get the energy from something else in order to actually harness and use that energy. And then when we do use that energy, we emit energy, and that energy is then reabsorbed by the universe. So this idea helps us define what a spontaneous process is. Spontaneous, what I'm talking about, is a process that is just going to occur really without outside intervention. So some chemical processes we know are not spontaneous. They require heat to be added, or a lot of stirring, or a lot of pressures, or something from an outside force, or other chemicals to be added in, catalyst most likely, in order for the reaction to actually occur. This doesn't mean a spontaneous process doesn't have to be fast. It can be incredibly slow. The turning of carbon into diamond is a spontaneous process. It happens over millions of years, but it's spontaneous. It doesn't really need an outside force other than the natural forces acting on it in order for that process to occur. There are many fast forms of combustion that are not spontaneous. If I want to do the hydrogen balloon experiment, that's not a spontaneous reaction. That hydrogen and oxygen gas will stay in that balloon forever, well, not forever, but for a very long time, without combusting, unless an outside force is acted on them, like the flame that's always on the end of my meter stick. So that's a very fast reaction, but it's not spontaneous. On the other hand, like I said, the conversion of diamond to graphite, really slow, but that is spontaneous. All right, so spontaneity. We need to define this term in order to get to the heart of spontaneity. And that's this idea of entropy. There are really two things that go into whether or not a process is spontaneous. It's enthalpy, which we've talked about. That's delta H, right? We've talked about that in the thermodynamics chapter. And then this other thing known as entropy. That's S, delta S. So entropy is a measure of the randomness or disorder in the universe. And the driving force for a spontaneous reaction, if a reaction is going to be spontaneous, is that we need to increase the entropy of the universe. So we have to increase the disorder of the universe in order for something to be spontaneous. Think about it this way. You take a wine glass and you push it off a table, it is going to break. Okay? Maybe that table will shake by itself. That wine glass really doesn't need any impetus other than the initial push to fall off the table, the activation energy to fall off the table and then actually break. And as it falls, as it hits the ground, it is going to break kind of all by itself. Now that's obvious, and we see that. That's an increase of disorder. There's this very ordered wine glass, it hits the ground, it becomes more disordered. And that certainly is something we can envision happening. What we can't envision happening is what the picture is showing. The glass then kind of reassembling itself back into a glass. That would be a non-spontaneous process. That would be a decrease in disorder, and that would be a different type of entropy change, a negative entropy change for the universe, and we just wouldn't think that would happen. Okay? So we think about spontaneity as being an increase in the entropy of the universe. So delta, a positive S of the universe equals spontaneous reactions or spontaneous processes. All right, let's talk about the easiest kind of depiction of entropy then, positional entropy. If we want to think about a high amount of disorder unorganized things having a lot of entropy, of a high entropy. We can think about it this way. The more possible molecular arrangements that a substance can have, the more disordered it might possibly be. More possible arrangements equals the higher disorder, equals a higher entropy. So let's think about the three most common phases of matter: solids, liquids, and gases. Solids, very, very organized, really don't have a ton of possible molecular arrangements, so they have very low entropy. They would have a less likelihood of actually occurring. Liquids, on the other hand, a little less organized, a little more randomness, a little more disorder, so they've got a little bit of a higher entropy. And then gases, I've got like the much, much greater than sign there, really high disorder, a ton of randomness, moving around all over the place, so they've got the highest amount of entropy. So they are the most random phase that we can have, and when we have spontaneous reactions with gases, gases are going to more likely form these spontaneous reactions because they're in that disordered state already. Okay, let's get to the second law of thermodynamics then, which deals directly with this idea of entropy. In any spontaneous process, there's always an increase of entropy in the universe. For a given change to be spontaneous, the delta S must be positive. The delta S of the universe must be positive. Now let me go back to the previous slide and just highlight something here. These, the liquid, the solid, and the gas, we're going to call those the S, or the entropy of the system. So let's just do something simple, like let's say water, for instance. We know that the system itself is the water molecule. So whether they be in the beaker or out of the beaker, if we could enclose them in a big balloon or something, that would be the system. The surroundings is everything else: the room, the city, the atmosphere, the planet, the universe. So for a given change to be spontaneous, the delta S of the universe must actually be positive. Okay? So if we go from the liquid state to the gaseous state, that is becoming more disordered. Our entropy is increasing. So for that to occur, the delta S of the system would be positive. Okay? So to go from the liquid state of water to the gaseous state of water, that's more disordered. Our system is more entropic, so it's a positive delta S for the system. Okay, but what about the surroundings? That's the question. What about the surroundings? Is that more entropic, or is it less entropic? And because we got to know this, because we want to know if we have a spontaneous reaction. We got to know if this is going to be positive or negative, which will then tell us whether or not a reaction is spontaneous. So let's look at two different examples here. We're going to predict the sign, delta S of surroundings and universe, for the following processes. Let's look at the process that I was just talking about. Okay, so we have a bucket of water here. Oops, let me go back here, guys. We have a bucket of water, and that water is being evaporated. It is going from the liquid to the gaseous state. Maybe we're boiling it. It doesn't matter. Okay, so we have these particles going from this state into this very, very random state. Okay, and I'm going to capture these particles in a big orange balloon. Here's my balloon. There it is. Okay, so everything you see in that orange balloon, this balloon right here, the green water molecules, everything that you see in there, that's our system. So we would say that the delta S of our system is actually positive, right? We don't know what that number is. This is a qualitative idea, not a quantitative right now. So the delta S of the system is actually positive. Now, what about the surroundings? Okay, let's think about that. Well, this system requires heat, so we have to take heat. Let's make the surroundings red. So this is the surroundings, right? We have to actually take heat from the surroundings. So surroundings heat goes into there, right there. So we're extracting heat from the surroundings. That's an endothermic process. So let's think about what's happening to the particles in the surroundings. If they are losing heat, if heat is coming out of them, then they're becoming slower. They're slowing down. Their kinetic energy is getting less. and they're becoming more random, right? This, guys, is an endothermic process, this whole heat loss from the surroundings. And so what do we have here? Our delta S for the surroundings is negative, okay? And if we looked on the previous page, if you remember from the previous slide that I have, we said the delta S of the universe equal the system plus the surroundings. So for this case, we have a positive plus a negative. Maybe I'll do that in the right colors, right? We have a positive here, positive plus a negative. So, do we know what delta S is going to be in this case? Do we know if it's going to be spontaneous or not? Well, we know what the surroundings are. The surroundings are negative, so we've answered this question. What about this one? We don't know, because it doesn't just depend on the sign, it depends on the magnitude, right? If delta S of the system is really, really big and really positive, and surroundings is really, really tiny, then sure, the delta S of the universe will be positive. But if the vice versa is true, then it's not going to be positive, and then it won't be spontaneous. So it depends on the magnitude. So this leads us to a second point with entropy. Entropy doesn't only depend on the heat flow, whether it's going into or out of something, it also depends upon temperature. Okay? And we'll get to see that in an example in the next slide. Let's think about the totally opposite now. Let's go the opposite way. So we've got CO2 gas, right? So you've got the carbon dioxide that you're breathing out, and we're gonna sublime it, or not sublime it. We're gonna deposit it actually the opposite way into dry ice or CO2 solid. Okay, if we can think of what's happening here now, we've got a totally different process going on. Here's your gaseous CO2. I'm gonna put it in a big old bucket. There's all my gas molecules. Okay. And what's happening here is you've actually got an exodus, right? You've got a slowing down or a more randomizing of emotion. And so in that case, we have heat actually leaving. So what's happening to your surroundings? Your surroundings are getting warmer. Okay, they're getting warmer. So your surroundings are a positive, but now since your gas molecule is actually becoming more organized, okay, this is actually a negative entropic idea. So you've got negative for the system. So again, it totally depends on the magnitude of these things. And it depends on temperature, whether or not this is going to be spontaneous or not. So at high temperatures, maybe this is not spontaneous. But at low temperatures, maybe it is spontaneous. Now, we got to be able to calculate that. Okay? So the sign of delta S of the surroundings depends on two things, as we've seen. The direction of the heat flow, is it exothermic or is it endothermic, positive or negative, okay? And also, so exothermic process, positive, right? Yeah, exothermic means that it's absorbing the energy, okay, from the system. So the molecules are going faster and faster, becoming more disorganized, so positive delta S. Endothermic process, be negative, be just the opposite. But the magnitude of delta S depends on the temperature. So we need to see how temperature is going to factor in on this. And the textbook actually goes through this derivation, and it says the delta S of the surroundings, or of the system in that matter, equals negative delta H divided by T. Negative delta H divided by T. That is what delta S of the surroundings equals. So it totally depends on our temperature, right? And we'll see an example of that, like I said, in a little bit. So the reaction spontaneity. Now what do we know? A reaction spontaneity, whether it's going to happen or not, depends on really two things. It depends on something we learned in a previous chapter called delta H, or the change in enthalpy, how much heat is absorbed or emitted from the reaction, and it depends on the organization and the order of delta S, okay, the entropy of the molecules. Well, it would be really, really awesome if we could combine these two things into a nice, tidy equation, and wouldn't you know it, we have done that. A gentleman by the name of Gibbs has done that process for us, and we call this the Gibbs free energy idea. So we've got another delta. So we've got delta H, we've got delta S, and now we have delta G. Remember, delta is change, right? Delta G is the change in free energy that will occur if the reactants in their standard states are converted to the products in their standard states. Delta G itself can't be measured directly, okay? Can't be measured directly, but we certainly can measure enthalpy change, and we now have an idea of how to measure delta S, which is entropy. Interestingly enough, Delta S is measured by understanding delta H, right? The more negative the value for delta G, the further to the right the reaction will proceed. Okay, so that's an important idea. I'll show you a table in a second that's going to hammer that home. And equilibrium, so the point at which we're at equilibrium, we're making the same amount of products as we are reactants, is the lowest possible free energy position for a reaction. Okay, so that's the point at which kind of everything is kosher. The forward reaction equals the reverse reaction. It's not that we have stopped the reaction. It just means that the stuff going in the front direction is equaling the stuff in the backwards direction. So here's a table that helps us define if something's spontaneous or not. I want you to go ahead and write this table down. I'm not going to go over each and every point, but it's just showing you if certain species in our equation, this equation right here, have certain values, if they're negative, positive, negative, or so on and so forth, how does that help us determine the spontaneity of the particular process? All right, let's do an example problem then with Gibbs free energy. Let me pull this guy up. And here it is. So we're going to ask the following. At what temperature is the following process spontaneous? At 1 atmosphere. Okay, that's our question. And here's the reaction. Oops, let me go back. And here's the reaction, guys. Let's see. There we go. Okay, so we've got liquid bromine that evaporates into gaseous bromine. That's nasty stuff, by the way. And we've calculated delta H of this process is 31 kilojoules per mole. And also the entropy change of this process is 93 joules per Kelvin mole. That, by the way, is the unit for entropy, a calculated unit for entropy. And if you check out the back of your textbook, you're going to see a whole bunch of those delta S's for different species. And it's in the same table as the delta H values for these species. All right, so we got delta H and we have delta S. Okay, delta S, by the way, is calculated the same way delta H is, by using that Hess's law idea. We'll see that again in the next video. All right, by the way, this question is kind of like asking this: what is the normal boiling point of bromine? Okay, we want to know the temperature at which gaseous bromine is produced from liquid bromine. Okay, so let's figure out how to kind of walk ourselves through this by using the idea of Gibbs free energy. We know this from our notes. We know that delta G equals delta H minus T delta S. Okay? So we want to know the normal boiling point of bromine. We want to know the exact point at which this stuff, the temperature of the following process, is spontaneous. Okay? So that exact point is going to be when delta G is 0, because that's when we're at equilibrium. Okay, if we go negative, that's going to be a spontaneous. If we go positive, it's going to be a non-spontaneous. We want to know the exact point at equilibrium. That's going to be essentially our boiling point of bromine. So we've got delta G equals delta H minus T delta S, and we do a little bit of rearranging here. Delta H equals a positive T delta S, right? Sounds pretty familiar. Okay, so we have to go ahead and plug in some numbers. Well, I suppose we could do one more rearrangement, right? Because we're looking for T. We're looking for this guy right here. So let's go to our final grand equation that we'll need is T equals delta H divided by delta S. And now we've got those two values, don't we? T equals delta H from the back of the book, 31 divided by, what do we got? 93, right? Is it 93? Okay. But remember, this is kilojoules on top, so this is kilojoules. I'm going to do a little converting. Why don't I do that right now? 31,000. Always watch your units. 31,000, there we go. Divided by 93. And if we find that out, then the temperature there is going to be 333 Kelvin, and that happens to be the exact boiling point of bromine. Very good. So that is the point at which this process is spontaneous, or what is the normal boiling point of bromine. So what do we know? We know that if the temperature is greater than 333 Kelvin, the term delta S controls the spontaneity. The increase in entropy when liquid bromine is vaporized is dominant, and so this process above 333 Kelvin certainly certainly will be controlled by the entropy. If T is less than 333 K, the process is spontaneous in the direction in which it's exothermic, and delta H actually controls the spontaneity. So if T is at 333 K, the opposing driving forces are just balanced, delta G equals 0, and the liquid and gaseous phases of bromine actually will coexist with one another. And this is now known as the normal boiling point. So there we go. There's a little idea of Gibbs free energy. 20-minute video. That's why we break them into two.